going to talk with you about sequences and series today. I think you've all seen a sequence and a series at least once in your lives, but maybe didn't know the ins and outs, or maybe didn't always know what you were seeing exactly. But let's focus on sequences first. A sequence is a function that computes an ordered list. And I think that's like the intuitive definition too that most of you probably already have in your heads. And with sequences, we'll just with pre-calc, we're going to be finding usually numbers or algebraic expressions, and then listing them with commas and separating the different terms out. You can have a finite sequence. A function that has a set of natural numbers as a domain. Of the form 1, 2, 3, etc. to n. You'll often see a lowercase n to indicate like how high up we want to go as far as the number of items in the list. Then you can have an infinite sequence. Has a set of natural numbers as its domain. So if you think about finite versus infinite, like finite, there's a cutting off. Like there's just a limited amount. Infinite, it keeps going on and on forever. So infinite, you're not going to see the in there, you're just going to see the ellipsis. Because it's going to indicate that it keeps going on and on forever like that. Okay. Now when we're trying to talk about these, we don't use the function notation f of x. We customarily use a sub n, where a sub n is the function evaluated at n. We often use the letter n instead of x, because n represents a natural number. The elements are called terms. Those are in the range of a sequence. And then those are thought of as a sub 1, a sub 2, a sub 3, etc. The elements of both the domain and range of the sequence are ordered. So that's an important point to keep in mind. And what else? What else do you need to know about these? You let, first n is 1, next n is 2, next n is 3, etc. general term is the nth term, so a sub n is the general or nth term. Okay, so let's look at writing some terms of a sequence. So a couple of examples. Write the first 5 terms of each sequence. So this is going to be finite, because we're specifically doing 5. And so for first one, we've got a sub n equals 5n minus 2. So we want to, so for our domain, n is 1, 2, 3, 4, 5. So we need to find a sub 1, a sub 2, a sub 3, a sub 4, a sub 5 for the first 5 terms. So notice that those n's are those natural numbers. And this is finite because it ends at 5. It doesn't keep going forever. But then we just take whatever n is and plug it in. So like a sub 1, n is 1. So 5n minus 2 becomes 5 times 1 minus 2. Or 5 minus 2, which is 3. A sub 2 becomes 5 times 2 minus 2. Or 10 minus 2, which is 8. A sub 3 becomes 5 times 3 minus 2. Or 15 minus 2, which is 13. A sub 4 becomes 5 times 4 minus 2, which is 20 minus 2, or 18. A sub 5 becomes 5 times 5 minus 2, which is 25 minus 2, or 23. So you would just list these as 3, 8, 13, 18, 23. That would be the first 5 terms in the sequence. So now let's say your sequence looks like this. A sub n equals negative 1 to the n plus 1 times n squared. And we want to find a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. So just where you see n, you plug in whatever your n value is for that particular term. So you got negative 1 to the 1 plus 1 times 1 squared. So negative 1 squared times 1. So 1 times 1 is 1. Then you got negative 1 to the 2 plus 1 times 2 squared. So negative 1 cubed times 4. So negative 1 times 4, which is negative 4. So notice this sequence, we're going to end up with alternating signs as we go forward in the terms because of that negative 1 to the power. Negative 1 to the 3 plus 1 times 3 squared. So negative 1 to the 4th power times 9. So it's going to be 1 times 9, which is 9. Negative 1 to the 4 plus 1 times 4 squared. So negative 1 to the 5th times 16. So negative 1 times 16, which is negative 16. And then finally, negative 1 to the 5 plus 1 times 5 squared. So negative 1 to the 6th power times 25 is going to equal 25. So you've got 1, comma, negative 4, comma, 9, comma, negative 16, comma, 25. So that's the first 5 terms of that sequence. So the domain included 1, 2, 3, 4, 5, that finite set of natural numbers. The range ended up being 1, negative 4, 9, negative 16, and 25. Okay. Convergent sequence converges, hence the name. In other words, the terms of an infinite sequence get closer and closer to some real number. So it converges to that real number, whatever that number is, it's getting close to. So an example, a sub n equals 1 over n. Well, if you start with n equals 1, you're going to have 1 over 1, or 1. Then you have 1/2, 1/3, 1/4, 1/5, etc. This particular sequence, as n gets bigger and bigger, it never actually reaches 0, but it gets closer and closer to 0. So it approaches 0 as n becomes large. So this is a convergent sequence that converges to 0. For those of you who are thinking about going on to calculus later, this is an important concept, convergent and divergent. Because not in calculus, you're going to see sequences in series again quite a bit, but also you're going to be talking about something called limits. And being able to see if something converges is going to help you with determining limits. So this will pop up again. If a sequence is divergent, it does not converge to any number. So the example is like, what if a sub n equals n squared? See, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, etc. It keeps going, it keeps getting bigger and bigger. It approaches infinity, but that doesn't count. It doesn't actually converge to a particular number. So that one's considered to be divergent. So as n becomes bigger, the values of a sub n do not approach a fixed number. Instead, they increase without bound. Okay, another definition, recursive. In this sequence, we say that the rule involves recursion. In other words, each term after the first term or first few terms is defined as an expression involving the previous term or terms. Really famous example is the Fibonacci sequence. This is a sequence that appears over and over again in nature, art, etc. I'm sure many of you have heard of it before. But this one, you start with 1, 1, and then the rule is you just take the previous 2 and add them together to get the next term. So you do 1 plus 1 is 2. Then you take 1 plus 2 and get 3. Then you take 2 plus 3 and get 5. 3 plus 5 and get 8. 5 plus 8 and get 13. 8 plus 13 and get 21. And so on. So that particular rule relies on previous 2 terms to get the next one. So that's a recursive sequence. So if you go out and look at flowers and plants, often things you can count petals, or you can count the numbers of spirals in the seed heads, and those often come out to Fibonacci numbers. If you take ratios of Fibonacci numbers, as you go down the line, it gets closer and closer to something called the golden ratio. Often we find things that the things that are aesthetically pleasing involve the golden ratio, like art and other elements of design. So that can be a cool little sequence to dive into. I also have a short video about it in my MGF 1107 playlist. So if you get a chance to check it out, it might be a little fun kind of diversion for you. Okay, so the Fibonacci sequence is not defined explicitly. If it had been defined explicitly, it would be like the earlier examples of sequences where the formula does not depend on a previous term. So since Fibonacci sequence does depend on previous terms, you can't say it's not defined explicitly. All right, let's try finding another sequence. Let's say you have a sub 1 equals 2. And let's say you have a sub n equals 3 times a sub n minus 1 if n is greater than 1. So a sub 1 equals 2, a sub n equals 3 times a sub n minus 1 if n is greater than 1. All right, and we're asked to find the first 4 terms. Well, a sub 1's already basically found for us. We know it's 2. But if we want to find a sub 2, we got to do 3 times, and when they say a sub n minus 1, that's saying go to the previous term, because n right now is 2, and 2 minus 1 is 1. So go back to a sub 1, which is 2 minus 1. So 3 times 2 is 6, minus 1 is 5. And then we go to do a sub 3. 3 times, well, a sub 2, which is 5, minus 1. So 15 minus 1, which is 14. And if we want to go do a sub 4, 3 times a sub 3, which is 14, minus 1. So 42 minus 1 is 41. So this sequence, the terms are 2, 5, 14, and 41 for the first 4 terms. So that's that finite sequence. But notice it depended on us going back and using previous terms. Okay, let's look at a little practical example. Okay, we have an insect population density. It's in thousands per acre. So we have an acre of land, and we're looking at how many thousands of this insect are on each acre. And then this is during year N. Can be modeled by the recursive sequence a sub 1 equals 5, a sub n equals 2.6 times a sub n minus 1 minus 0.25 times a sub n minus 1 squared for n greater than 1. So a sub 2, a sub 3, a sub 4, etc. So if you're trying to find the population for n, like n equals 1, then it's 5,000 per acre. We know that because of a sub 1 is 5. If we want to find the population for n is 2, trying to find a sub 2, which would be 2.6 times a sub n minus 1, which would be a sub 1, or 5, minus 0.25 times 5 squared. So when I worked that out, 2.6 times 5 minus 0.25 times 5 squared, I got 6.75. And like if you want to do it for n equals 3, a sub 3 equals 2.6 times the 6.75 from a sub 2 minus 0.25 times 6.75 squared from a sub 2. If you do that, you get approximately 6.16. Now, as it increases, I'll leave it up to you to keep doing more. As it increases, if you keep doing more of these, you're going to find that the population density oscillates. Above and below. A number. And we can find that number by using a k, like a variable, up there in that a sub n model. So what we can do is, instead of saying a sub n and all that, we can say k equals 2.6k minus 0.25k squared. We want to figure out where it can converge to if you keep going, as it gets bigger and bigger. So let's see, I moved the 0.25k squared over. I also subtracted 2.6k, 1.6k, factored out k. Of course, k equals 0 for one of those. That's not what it oscillates around. If you solve the other, you get k equals 6.4. So it oscillates above and below 6.4 thousand insects per acre. It converges near to this. So it's not saying it will necessarily reach that number, but it's going to get closer and closer to it. Going to go up and down, above, below, but it gets closer and closer to that as your n gets bigger. So as years go by. Okay, so that's sequences. Now let's get into series. I'm going to introduce some new symbols. Okay, finite series. It's an expression. We'll use S sub n, where you basically take this. You take the terms of a sequence and add them up. And you can write this using something called summation notation. You're going to use the Greek letter sigma. And in math, sigma means summation. So you can do this. You can do a little summation symbol. And you can use like the letter I. You know, like this is not like I for imaginary. This is just generic I. But you could use K or J. You can use whatever letter you want. And you could say, well, I equals 1 to n of a sub I. So what this notation is saying is, like, you take A and you start with I being 1, and you take A and do 1, a sub 1, then you do plus a sub 2, then plus a sub 3, and so on until you get to the top one, which is a sub n. And that summation means you add up all the results. Infinite series, well, it's just what it sounds like. You can use s sub infinity. You're still adding up those terms of a sequence, but remember now you're dealing with infinity. So you're not going to stop at a sub n, you're going to keep going past that forever. So you can use that little Greek summation symbol again if you'd like. You could say I equals 1 to infinity of a sub I. That little letter I is the index, called the index of summation. So again, that's not I like imaginary, that's just a little index. If plural indices. Okay, so how would we see this in practice? And again, it doesn't have to be an I, it can be a J or a K, you know, some other little letter. So like this one says J equals 1 to 5. And then the expression is J squared plus J plus 1. So what we got to do is, starting with J equals 1, use that expression, 1 squared plus 1 plus 1, which is 3. Then for J equals 2, we're going to have 2 squared plus 2 plus 1, 4, 6, which is 7. J equals 3, we're going to have 3 squared plus 3 plus 1, which is 13. J equals 4, 4 squared plus 4 plus 1, which is 21. J equals 5, 5 squared plus 5 plus 1, which is 31. So we just found the terms in the sequence, but we're trying to do a series here, so we got to add those up. We got to do 3 plus 7 plus 13 plus 21 plus 31. And that comes out to 75. So that's your answer after you add all those up. So we're dealing with the J's, are natural numbers from 1 to 5. And then you're substituting them into the expression there next to the sigma. And then when you're done getting all the, each time you do that, it gets you a term in the sequence. And then when you're done, you add up all those terms to get the final summation. So then you're dealing with your series. Okay. Let's do a couple more examples of that. Like let's say you have summation of I equals 1 to 5 as b sub I. So that would be b sub 1 plus b sub 2 plus b sub 3 plus b sub 4 plus b sub 5. That's it. There's nothing else we can do with that one. Because the expression is b sub I. We don't have anything to plug in for b. And then I is the natural numbers from 1 to 5. And it's a summation, so you got to add them all up. You'll find I'm kind of lazy. Sometimes with my summations, I kind of scribble them. Let's say you have j equals 1 to 4, summation from j equals 1 to 4 of 2x sub j minus 5. And we're told if x sub 1 equals 3, x sub 2 equals 5, x sub 3 equals 7, x sub 4 equals 9. Okay, so when j equals 1, that's 2x sub 1 minus 5. Well, we know x sub 1 is 3, so that's 2 times 3 minus 5. 6 minus 5, which is 1. When j equals 2, that's 2x sub 2 minus 5. Well, we know x sub 2 is 5. 2 times 5 minus 5. So 10 minus 5 is 5. J equals 3. 2x sub 3 minus 5. So x sub 3 is 7. 2 times 7 minus 5. So 14 minus 5, which is 9. J equals 4. 2x sub 4 minus 5. So 2 times 9 minus 5. 18 minus 5, which is 13. So then our final job is to add up all those terms. 1 plus 5 plus 9 plus 13. And I get 28. So I found each of the terms, and then I found the summation. Okay, let me give you some properties and rules which can help make things a little easier. We're not going to prove them. I mean, if you're really interested in proving the properties, some of it can be seen in your book in this lesson, and then some of these others can be proven later after you learn something called mathematical induction. But here's some summation properties. Might make your life a little easier sometimes. Let's say you're summing I equals 1 to n, and you just have some constant c. Basically, this is saying you're adding up c n times. So a real quick shortcut would be to do n times c. Because like, let's say you're adding up I equals 1 to 4 of 5. Then it's saying you're adding up 5 4 times. So you can just multiply 5 times 4. If you have a constant c, and keep it in mind that a sub 1, a sub 2, all the way to a sub n, b sub 1, b sub 2, all the way to b sub n. Keep in mind that these are two sequences. So when you see a's and b's, we're dealing with sequences there. C is still a constant. But you can put the constant in front of the summation. It's kind of like factoring it out, really. So you can find your summation with the sequence and then multiply by the constant. I mean, you could do it the other way too. You could do constant times each term and add that up. Or you could factor out the constant and do the summation first before adding it up. So that could be very helpful. If you have a summation of two sequences, you can break it up into two summations. As you think about it, it's all addition in this case. So like if you're adding 1 plus 2 plus 3 plus 4 plus 5 plus 6, you could add them all up as is, or you could add up 1, 3, and 5, and then add up 2, 4, 6, and add those together. So you could group them differently if you want to. Whole associative property idea. Or if it's a subtraction, you can also break that up. Because it's like you're putting the negative 1 in front of the summation, that second summation. So it's similar. It's kind of like combining the property with the constant and the property with the addition. You could factor out the negative 1 constant, put it in the front, and then break, and also like at the same time be breaking it up like you did just above that with the addition. So let me show you an example there. Let's say you have the summation of I equals 1 to 50 of 12. You could sit there and add up 12 50 times. But why do that when you could do 12 times 50 and get 600? So that's just something to keep in mind. If you have something like summation of I equals 1 to 35 of 3i, you can put the 3 out front and do summation of I equals 1 to 35 of I. Now from there, if you really want to, you can add up 1 to 35 and then multiply by 3. But in a minute, I'm going to show you another rule that will help you make that faster. So let's just pause on that. If you have I equals 1 to 10 of 3i squared plus 5, you're allowed to break that up. I equals 1 to 10 of 3i squared plus I equals 1 to 10 of 5. But don't forget, you can break that up a little further. You can put the 3 out front here. 3 times summation of I equals 1 to 10 of I squared plus, and then there you can do 10 times 5. Now I'm going to show you a rule that can help you with summing this I squared faster. I mean, you could sit there and do 1 squared plus 2 squared plus 3 squared all the way up to plus 10 squared and then multiply by 3. It's up to you. Or you can hang tight and in a minute you'll see a rule that'll help you with that. Okay, so some summation rules. For these, again, you need mathematical induction in order to help prove that they work. We're not going to get into that right now. Just accept that they work. If you have summation of I equals 1 to n of I, in other words, you're adding the numbers 1 plus 2 plus 3 plus 4 plus 5 all the way up to whatever your n is. So you're adding up natural numbers all the way up to your n. That can actually be done quickly with the formula n times n plus 1 over 2. Carl Friedrich Gauss, I don't know if you've heard the story before about him, but he was a very bright young man. And when he was about 10 years old, he was in class and he was getting work done quickly and asking a lot of questions. And the teacher decided to try to give him a little problem to do to keep him busy for a minute because she had other students to work with too. So she asked him to go over and add up the numbers 1 to 100. I'm like, okay. So, she went over to his desk or wherever, and he didn't take too long, and he came back, and he told her the answer was 5,050. It's like, what? Well, he's adding the numbers 1 plus 2 plus 3 plus 4 plus, all the way up to 99 and 100. So what did he do? Well, he figured out that you could pair them up. Like 1 plus 100 is 101, 2 plus 99 is 101, etc. And he figured out there's 50 pairs like this. So 50 times 101, which gives him 50/50. He saw that pretty quickly. But your formula kind of helps you with that. Because, basically, he was taking I equals 1 to 100, summing the i's. So you have 100 times 100 plus 1 over 2. Oops, sorry. I don't know why I wrote 20. 2, not 20. No idea why I wrote that. There you go. So 100 over 2 is 50, and 50 times 101 is 50/50. So your formula gives you the same, basically does the same thing for you. Pairs them up like that. Okay, another summation rule, as promised. There's 2 more I'm going to show you. I equals 1 to n of I squared. So that's 1 squared plus 2 squared, all the way down to n squared. You can do n times n plus 1 times 2n plus 1 over 6. And then for I equals 1 to n of I cubed, so that's like 1 cubed plus 2 cubed, all the way up to n cubed. You can have n squared times n plus 1 squared over 4. So these can help us further with some of those problems earlier. So remember the problem with I equals 1 to 35 of 3i. I had said, well, you could do 3 times summation of I equals 1 to 35 of I. Oh, we did that one already. Well, no, we did. Okay, so 3 times, and then we have that new rule now for summation of 1 to n of I. We can do 35 times 35 plus 1 over 2. And when we do that, we end up with 1,890. And then for our problem with summation of I equals 1 to 10 that I did earlier, we had 3i squared plus 5. We had broken that up into 3 summation I equals 1 to 10 of I squared plus, and we had a 50. We figured that out earlier. But now we can do that summation with the I squared. 3 times, we could have 10 times 10 plus 1 times 20 plus 1 over 6. And figure all that out, plus 50. So when you do figure that out, you get 1155 plus 50, which comes out to 1205. So I'll let you do the math, the basic math there, but so you can finish now those 2 problems. Okay, let's do one more. Sum of I equals 1 to 5 of I cubed plus 2i minus 8. We've not done this one yet. So we can break that up into sum of I equals 1 to 5 of I cubed plus sum of I equals 1 to 5 of 2i. We can say minus sum of I equals 1 to 5 of 8. So the I cubed, since 1 to 5, n is 5, we can do 5 squared times 5 plus 1 squared over 4. So 25 times 36 over 4. So that gave me 225. Plus, we can do 2 times the sum of I equals 1 to 5 of I. So 5 times 5 plus 1 over 2. So basically 5 times 6, which is plus 30, because the 2's cancel. And then down here, you just basically do 5 times 8, which is a minus 40. And when we do that, add them up, we get 215. So just using our lovely rules to make things a little faster. You could sit there and add up every term, like I equals 1 to 5 of I cubed. You could sit there and add up 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, and you would get 225. For I equals 1 to 5 of 2i, you could add up 2 plus 4 plus 6 plus 8 plus 10. You'd get 30. For I equals 1 to 5 of 8, you could add up 8 5 times. You'd get the minus 40 there. And then you end up still with the 215. But these rules can make things a lot faster. So I would say make sure you familiarize yourself with those, the properties and the rules. All right, so I think that was a good introduction to sequences and series. We're going to get a little more specific in one lesson with arithmetic sequences in series, and then with another lesson with geometric sequences in series. So we're not done yet with these, but we're going to have some more fun with them and getting more specific about some certain types. And then go from there. All right, so I think that's enough, though, for today. Thank you for joining me, and I look forward to seeing you again with sequence and series fun.